You might have seen this video of 3 blue, 1 brown drawing stuff using Fourier circle things. Well, I just made it in Desmos. So, here's what happened. I woke up one day, remembered that Fourier series and Fourier transforms exist, and wanted to build something cool out of it. Specifically, I wanted to build the rotating circle thingy, making a portrait of Joseph Fourier, which is pretty cool, right? But we can't just directly dive right into the building phase yet. We need to understand a few of these fundamental questions before proceeding, starting with what is going on. So, these Fourier circle thingies are formally known as Fourier Epicycles in maths. And Fourier Epicycles are based on the principles of Fourier series and Fourier transforms, which we are going to explore in this video. So, we'll explore them one by one, starting with Fourier series. Now, I learned this during my electrical engineering course, and I'm going to explain it to you in the same context. And after that, we'll build up using that definition towards creating complex shapes using rotating vectors. And if you want to find out, you should stick around with me. So what are we waiting for? Let's jump right into it. So let's take some arbitrary electrical signal, which is a voltage over time curve. It would probably look something like the image on the left. Now, this voltage over time curve or signal can be expressed as a function of time. So, I'm going to denote it using capital F of t. Now, what Fourier series allows us to do is write this capital F of t as the summation of a bunch of cosines and sines. This can again be simplified into just a summation of sines wherein each sinusoid has these three parameters: frequency, amplitude, and phase. By tweaking a list of these parameters, we can create, in theory, any continuous function. I should also add that this is used to create any periodic continuous function, but if you take an infinite series, in theory you can create any function from this. But I can't create a circle using that now, can I? Because the output of capital F of t right now is a real number. You need to understand that the perception of the problem is a bit different from just graphing things, right? We are trying to guide a point through some n-dimensional space, preferably 2D here, using our capital F of t function. And if the output of that function is a real number, we can only guide it through 1D space. So, what we need is to change the output of capital F of t into something that can guide a point through 2D space. And if you were wondering that we just drew a signal earlier, that's 2D, right? No, that's just a plot of the 1D movement of that point against time, which if we are trying to use to create some of those complex geometries is pretty much impossible. So, here's a cool demonstration of what was really happening. You can see the white point is what we are going to get by, when capital F of t is going through time. That is the motion, and which is not what we want. That's pretty boring. That ain't gonna draw anything, right? So, what we really need is a point being guided in 2D space by the function of time. And then we can take its locus to give us a desired shape. Now, doing that is actually pretty easy than said, because what we say is a point in 2D space can simply be represented using a complex number. So, all we need to do is change the output of capital F of t to be complex. And that can be done pretty easily when you realize if you take the amplitude of a sinusoid as complex, the output of the whole function will become complex. Essentially, you're granting the freedom to an. So, putting that into our previous equation, we get this. Okay, that's not really what we wanted. We thought that we would get rotating vectors, but this is some spring elastic thing. I don't know what this is. This is not what we want. Where are the circles? Okay. To get to circles, we need to do some clever math. Okay, so to get circles, if you know any math, you would be probably thinking of this format. That's right, we use Euler's identity because that is what helps us create rotating vectors. We break down the an into the format shown and the sign as well to this long expression, and I would like you to take a moment here to appreciate this math. If you want, you can actually go ahead and multiply and simplify the terms to see what you get. You can pause the video to do so, and if you've gotten the answer, here's what you're gonna get. Two terms of the form are e to the power I 2 pi ft plus pi. That is exactly what we were looking for, rotating vectors. As you can see in this demonstration I've made in Desmos, where I've used an example vector 2e to the power I 2 pi a, this is how a rotating vector looks like. Cool. So, since we have a rotating vector, we have that equation. All we need to do is superpose a bunch of these vectors and we are good to go. So, we just change the equation to this equation, and basically it's not forwards, we are using it backwards. If you see, what we are actually doing is taking the rotating vectors, summing them up to create some f of t. And how do we do that? Using these parameters. Since a rotating vector is essentially defined based on only these three independent parameters, we can just tweak these parameters using some lists, of course, and create cool shapes. Now let's see an application of the same in Desmos. Alright, so this is actually the first implementation of the Fourier thing that I did in Desmos. The implementations is actually pretty easy. All you need is these three lists, as you can see. The list of W, which is angular frequency, B for biases or phase, and A for the amplitudes or the radius of these circles. And apart from that, the main function, which is the main valuable player here, it is this function f of a. This function right here is basically what we discussed in this video and what we derived to. But you might be wondering where the e to the power I theta format is. Actually, I didn't know Desmos had this complex mode as well, so I broke it down into its cos and sine components to write it as points. Other than that, we have this here. This entire part is just for the UI to draw these beautiful circular things and these arms that makes it appear as if it's drawing. You can see it like this. So these arms and these circles, that's what this section right here is for. And yeah, that's pretty much the implementation. So now that we have covered the Fourier series, we have reached our halfway point. We learned how and why rotating vectors can be used to create complex shapes, and even saw an implementation of the same in Desmos. But we can't always rely on hard-coding the list to get shapes, because how do you explain the portrait of Joseph Fourier that was shown at the beginning of this video? Now, to do all of that, you need to stay tuned because we'll be dropping a part 2 of this video series very soon. And if you like this video, be sure to drop that like button, share this video, and subscribe to the channel. And don't forget to give your feedback in the comments, and I'll see you in the next one. Bye.